All right, welcome to section 10.3. By the way, this should be the 5th video that you've seen. This is not the 3rd video. If this is only the 3rd snow day, you skipped a couple. There were videos for the first 2 sections, but then 2 days worth of AP free responses. So this is only the 3rd snow day. Make sure you go back and find the day 3 video going over the AP free responses. But day 5 now, we're going to start looking at a totally different way to graph points and equations. Instead of using x's and y's on what we call our Cartesian coordinate system, this is the polar coordinate system. The polar coordinate system measures things not in x's and y's, not in horizontal distance and vertical distance, but rather in length, or like an r value, and then theta, an angle measure. So this is what the polar coordinate system looks like a big old bullseye, like a big old target. And I'm going to just show you how to plot a few points on here first of all. The r, you can kind of think of it as a radius, and then the theta obviously is going around, kind of like the unit circle does, exactly like the unit circle does. Starting at 0 here, going around pi over 2, pi, 3 pi over 2, and then that'd be 2 pi again. So if I wanted to plot a polar coordinate, let's say I wanted to do 3 pi over 6, let's say. The 3 is the r, it's the radius going from this middle point, which we call the origin normally. It's called the pole in polar coordinates, but it's still the same idea of the kind of the center of the graph. So from here we would go out 3, so like each of these rings is counting for 1. So like we go out 1, 2, 3. That would be the length, that'd be the distance from the pole. But as far as where to put this on this circle, that's where that angle comes in. This pi over 6 is, go to where the angle pi over 6 is, like on the unit circle that you're used to. It's like if this is 0 and this is pi over 2, pi over 6 is here. So go to the angle of pi over 6, and that point should be 3 units from the pole. So on the pi over 6 here, go out 1, 2, 3, and here's where that point is, 3 pi over 6. It's not an x and a y, although we will convert this to x's and y's here in a minute. This is a radius, a distance from the pole, and then an angle measure. So if I wanted to do another one, let's say, over here some. Let's do, oh yeah, I forgot the bells are ringing, because you know, you want to ring the bells when there's nobody at school. Let's say I wanted to have, the r is 4, and this angle measure is going to be 3 pi over 4. So find my 3 pi over 4, should be halfway between pi over 2 and pi, so that looks like that's here. And then from the pole, go out 4. 1, 2, 3, 4. Here's that point, 4, 3 pi over 4. That would be the one way to write those coordinates. It's actually a different way to write each of the coordinates because you can have the r be negative. Like here, let's say I wanted a different way to write this equation, or this point, sorry. Instead of thinking about pi over 6, I could think about the other angle through here, which I guess would be 7 pi over 6. And instead of going 3 units towards 7 pi over 6, I could go 3 units away from 7 pi over 6. And I could make this r a negative 3. So another way to write this point would be negative 3 and 7 pi over 6. The angle would be 7 pi over 6, but instead of going toward that angle, you go 3 units away from that angle, basically back through, reflected through the pole. A different way to write this point would be a negative 4, and then whatever angle is down here in quadrant 4, so I guess that's 7 pi over 4. Like that. Most likely you're going to see r's be positive when we start to get into AP problems, but I wanted you to see that there's actually 2 different ways to write these coordinates. Technically, if you wanted to start talking about angles that are bigger than 2 pi, you could call this 13 pi over 6. And and so on. But generally things are measured between 0 and 2 pi. But this r can be negative sometimes. So that's what your polar coordinate system looks like. Since you had never seen one at all, I wanted you to see what the actual graph looks like. And now I'm going to try to do a quick change here because I have other things behind here. This could be tragic, by the way. So like get your Vine stuff ready or your screen caps ready because something awful could happen. Oh, so far so good, I think. All right, let's see if I can get this zoomed back in to where you can actually see it okay. Let's see here. Sorry if that just meant this is making you dizzy. All right, I'm going to try to get the polar coordinates. That seems reasonable. Now I have something that would be a polar coordinate. See that r and that theta there, and I want to change it to a Cartesian coordinate. I want to change it back to x's and y's. Now I'm going to go back to something that you kind of have connected the like the unit circle with, and hopefully that's going to help you figure out how to do this pretty quickly. So if I had 6 and then pi over 3, so if I go back to what my polar graph looked like, think about where pi over 3 is. Pi over 3 is about up here, and you'd be going 6 units away from that pole. And so that point would be up here. All right, so that's where that point would be in polar coordinates. We want to talk about the Cartesian coordinates, the x's and the y's that go with that. You know something about the connection between these two coordinate systems because you know the unit circle really well. Most of you know the unit circle really well. So what you know about the unit circle is that if I were to pick a point anywhere on the unit circle and say, okay, go back here, the radius is 1. If you pick some point on that unit circle, you know that the x value stands for the cosine of that angle. And you know the y value is the sine. You know cosine is x, you know sine is y. You learn that. A lot of you just use the unit circle to memorize those values back in the day. So if the radius were just 1, you would know how to take, like if this were a 1, you would know to go to this angle, and the cosine of this angle would tell you the x value, the sine of this angle would tell you the y value. The only way that the r, the radius, changes this is that it multiplies that cosine angle, the cosine value by whatever that radius is. So the x coordinate here is not just the cosine of theta, it's the r times the cosine of the theta. So if I'm looking for this point here in x's and y's, I can get the x coordinate by doing the radius times the cosine of your angle theta. We know cosine of pi over 3 is 1/2. We know 6 times 1/2 is 3. So 3 would be the x coordinate of our point. The y coordinate is the radius times the sine of theta. These are really valuable to us later on. All right, so 6 times the sine of pi over 3, 6 times radical 3 over 2 would be 3 radical 3. So that point, 6 comma pi over 3, that's the same point as 3 comma 3 radical 3 on our Cartesian, on our x's and y's. Right? Just by taking r times cosine of theta to get x and r times sine of theta to get y. So make sure you know these conversions. It's just your unit circle stuff you already know multiplied by whatever the radius is of those things. So it's not too bad to change things from polar to Cartesian coordinates. Changing from Cartesian to polar is a little bit trickier. And I've got hopefully an example here. Don't fall down. Good. If I've got a Cartesian coordinate of 5, 5, and I want to change that to polar coordinates. So here, I say, all right, I've got this point at 5, 5, but instead of writing this as x's and y's, I want to think of it as a polar deal. So I need to know the angle where that would be. And hopefully you can kind of see, since I did this on purpose, since the x's and the y's are the same, you know, this should be right at pi over 4. That should be what our theta comes out to be, and that will happen at the end. And then the r is the distance from, we call it the origin here, we call it the pole on polar coordinates. It's the distance from this point to the origin. And you'll recognize that as a little bit of Pythagorean theorem again. If this is 5 and this is 5, to get that hypotenuse there, you do the square root of x squared plus y squared. Right? That's just the Pythagorean theorem. And if this were 5 and this were 5, you probably don't need to do all this business. You say, well, that's clearly 5 radical 2 would be your r value. The distance from the pole out to that point, this distance here would be 5 radical 2. That's your r value. To get your theta value, you do this, you do the arctangent of y over x, which seems a little random, but it's not random at all. Because think about what you know about y and x on your unit circle. Y stands for sine, and x stands for cosine. So if you do sine over cosine, that would be the tangent. So y over x would tell you the tangent of whatever angle you have. So like 5 over 5 would be 1. 1 would have to be the tangent of the angle. And then you do the inverse tangent to figure out what that angle would be. So in this case, theta is the inverse tangent of the y-coordinate over the x-coordinate, 5 over 5. It's the arctan of 1, which means find the angle that has a tangent of 1. We know that angle is at pi over 4. We know the tangent of pi over 4 is 1. So we could take that point 5 comma 5, and as a polar coordinate, write it as 5 radical 2, basically the hypotenuse of this right triangle, and then the angle, theta, would be pi over 4, the arctan of y over x. Again, y over x, sine over cosine, gets you that tangent expression. So that's how you convert something from Cartesian to polar coordinates. So now we can swap from one to the other, Cartesian to polar, polar to Cartesian. Now, a little bit of calculus to finish up this first polar coordinates video. And let's start with just doing derivatives, because I think you can probably guess how we go about doing this. Now, say, okay, we're given this is a polar equation. It's not in terms of x's and y's, it's in terms of r's and thetas. What that graph looks like, something weird. We might explore some of the graphs. You'll see a couple of them when we get to the AP problems, but these polar coordinates can be really strange looking graphs. You can get infinity looking signs and like heart shapes. There's loops and all kinds of crazy things. But we want to know the slope of the tangent line to this equation when theta equals pi over 3. So we need to take the derivative of this thing. And so we're talking tangent lines now. We're talking x's and y's. So we have to convert from what we have here, from the r's and the thetas. And if you remember what we did with parametric equations, with that t in there, we said we'd call this, to find dy dx, we do dy dt, and we divide by dx dt. You do a similar thing here using theta instead of t. So to find dy dx, you're going to do dy over d theta over dx over d theta. If you go back and think about derivatives of parametric things, we found dy dx. It's the exact same concept, only now there's a theta here instead of a t. Parametric equations deal with time, polar equations deal with angles. So we need to be able to find dy d theta and dx d theta. Now we don't immediately have x's and y's in this equation. Here's where we have to convert and figure out like what the y value is and what the x value is of this thing. So that to find the x value here, that I'll have to take the derivative of, this is where we use our r cosine theta again. The x component of this is always r times cosine of theta. So in this case, that would be r, and this is r, 1 plus sine of theta times cosine theta. And the y-coordinate is going to be r times the sine of theta. R is 1 plus sine theta here. just substituting that in, times the sine of theta. Now you are welcome to start trying to simplify this if you want. I don't recommend it because we're going to end up taking the derivative of both of these things. This is x, this is y. So to get dy d theta, I'm going to take the derivative of this expression with respect to the variable theta, and the same with the x's. I would rather just do the product rule here as opposed to trying to multiply this out and then like sine squared theta, the chain rule would get involved. Maybe identities start to get involved, which I know you don't want to deal with if you don't have to because we've forgotten all but one of them. So I would recommend just leaving this as is and then taking the derivative. So here, if this is y, I want dy d theta here. I just do the product rule. Derivative of the first part, so that's going to be cosine theta times the second part, plus the first part times the derivative of the second part. Over here. That's dy d theta. Then dx d theta, I want to take the derivative of this with respect to theta. So the derivative of the first part times the second part plus the first part times the derivative of the second part, like that. That's dy d theta over dx d theta, which if you kind of think of it algebraically and you think of those canceling, you'd have dy over dx. That's your derivative. It's ugly. You're better off not simplifying it. And now we're going to have to plug in pi over 3. That's not going to be pretty. Let me just pause. I really appreciate you watching these videos at home. Here's what I'm going to do. So I've got 100 bonus points here. If you email me sometime before midnight of this 5th snow day, I will give you some of those 100 bonus points. If you are the only person who emails me, I will give you 100 bonus points. If you're the only person watching this video, you get all 100 points. If other people are watching and email me as well, I'll split them up. If 10 people email me, you each get 10 points. So don't go tell people, don't go tweet it out that they're supposed to email me. Just email me sometime between now and midnight and say, give me some points. And after midnight, I'll just see how many people and who's emailed me, and you all get part of the 100 points. Because I really appreciate you all doing this on your days off. And it's going to pay off May 9th when we do the AP exam, because you guys will do great on this stuff, and a lot of schools won't have seen it at all. All right, so back to the show now. We've done dy d theta over dx d theta. We're going to have to plug in pi over 3 everywhere here. I'm going to erase this, I guess, just so I have somewhere to plug that in and I don't have to use another board. So if this is my derivative, I'll get rid of this. And I'm going to plug in everything that I know. Cosine of, so I'm putting in pi over 3 everywhere there's a theta. You're going to have a calculator. I can almost guarantee it. So you really aren't even going to need your trig values here. You're just going to be able to go directly into typing this into your calculator. I'll go ahead and do this since we know pi over 3. But I'm not going to simplify. I'm not going to do the arithmetic after this. This is a negative sine of pi over 3. Don't forget about that negative sign. All right, so now, let's see. I know cosine of pi over 3 is 1/2. I know sine of pi over 3 is radical 3 over 2. I'm going to substitute that in everywhere. Oops. Go away. And then cosine of pi over 3 is 1/2. This is 1/2 times 1/2. 1 plus radical 3 over 2 times negative radical 3 over 2. So there you go. I would leave my answer like this. this actually all simplifies out, and I only know this because I stole this example from the book. This comes out to -1. If you've done all your homework problems and you're still bored and you want to try to figure out how this thing comes out to equal -1 and you want to work it out, then I'll give you some more bonus points if you really want to do that. I don't think you want to do that, though. I feel like there's something better you can do with your day. And I definitely want you to do the problems in the packet. I definitely want you to do the section 10.3 problems so that you get used to finding derivatives of these. Don't get hung up in the arithmetic and the algebra of it. Worry about figuring out how to get x and y by doing r times cosine theta, r times sine theta. Worry about taking the derivative. Then you can plug in everything from there. When we get to the AP problems, you'll see the key parts are being able to do the calculus and just sort of set things up and make the calculator do all that ugly stuff. So have a great day, and we will see you soon.